Hi, welcome back. In this lecture, I would like to talk about an important quantum circuit called phase kickback. Somehow the phase kickback quantum circuit is very similar to the base pair quantum circuit. At the very least, it has very similar working. The way that is going to work is the following. We're going to have a control operation. In the case of phase kickback, is going to be a control phase operation. And also we're going to put the control qubits in a superposition of state. The interesting effect of the phase kickback quantum circuit is the fact that the control qubits also are going to be affected by the operation of the quantum circuit. But let's start talking a little bit about the phase kickback. So altering the phase of one qubit register condition on the values of the qubits in some other register that are in superposition, we can produce a surprisingly useful effect known as a phase kickback. In the phase kickback quantum circuit, we're going to have our control qubit system. In this case is a 2-qubit system, register 1. We call this is going to be the control qubit system. And then we have our target a qubit system that is register 2. In this lecture, I talk about a specific realization of the phase kickback in the textbook, on the web. On the web, you can also find a different realization of the phase kickback. However, the technique is very similar, the one present in these slides. After placing register 1 in a superposition of 4 states, since this register 1 consists of 2 qubits, so then we have 4 possible states. We're going to put in superposition the Hadamard gate, and then we're going to apply a condition phase rotation on register 2. So we apply 2 condition quantum operation on the register 2 that is, remember, is our target. So the important part about the phase kickback is the fact that our register 1, that is our control qubit, has been affected by this operation. You see here a change of the phase on the quantum state. So the phase rotation that we try to apply on the second register, on register 2, our target condition on the qubits from the first, has also affected the different values on the first register, that is our control register. Let's look step by step. The step in our quantum circuit that is producing a phase kickback in the control qubits register. The first part is just the initialization of our quantum system. We can visualize it as a 3-qubit system as the following. All right, so we're going to have a register 2 that can have only 0 and 1 value, and then the register 1 has 4 values. This is the combined view of the register 1 and register 2 using 3 qubits. After the initialization, we can apply 2 Hadamard gates on the register 1 qubits. And you see this applying these quantum gates on the 0, we will see that we put register 1 in a superposition of state. So each state will have equal probability of being observed. Then if we apply a first C phase of 45 degrees, we see that the C phase only works on the state 1 and 3, so we apply a relative rotation corresponding with respect to the 0 state. All right, so this is for the 1 and the third on the third values for the registered 1, where the binary notation has 1, 1. Those are the selected one. Then we apply another rotation. In this case, we the particularly controlled qubit, and also we change the phase. By applying this C phase operation, then at this point we affect only the values 2 and 3, and these are rotated by 90 rotation. The net results that we see in register 1 is the combination of the phase rotation that have been kicked back from our target into the control register. Phase kickback is very useful quantum circuit, as we can use to apply phase rotation to specific values in a register. We can do this by performing a phase rotation on some other register conditioned on the qubit from the register we really care about. We can choose these qubits to specifically pick out values that we want to rotate. An important aspect of phase kickback quantum circuit to work, so to apply this phase rotation on the control qubit, is that we initialize register 2 in state 1. If we try to initialize register 2 with 0 state, this is not going to work. This is the 3 qubit notation. You see there is no rotation at all in the quantum state of our 3 qubit system. So for phase kickback to work, we always need to initialize the second register in the 1 value. Note that although we are applying a 2 qubit operation between the 2 registers, the 2 registers are actually separable, so there is no entanglement. So we can fully represent the state as a separate register. A final important note for this lecture before I finish up is that 2 qubit gates do not always generate entanglement between registers. Obviously, we look at 2 qubits system that are interesting, the Bell pairs, the phase kick, in one case we saw entanglement, in this case we didn't see entanglement. So it means also 2 qubit might or might not produce entangled state. This is the last slides of this lecture, and talk to you soon.